Hey physics kids, in our last video on magnetism, we're going to talk about electromagnetic induction, or Faraday's law. So remember I've talked a bunch about Ørsted and about how he, through accident, found out that running current through a wire creates a magnetic field. Well, Faraday wanted to know, hey, well, if current create a magnetic field, can a magnetic field create current? Hey, electricity. So he set up this little setup here where he had a battery connected by a wire with a switch to an iron core here. This is an iron ferromagnetic material, but not magnetized. And he had that set up to an ammeter. The wire, here we go. And what he did is if current generated from a battery created a magnetic field, would that create current in this other wire? And an ammeter, right, detects current. So he flipped the switch and he looked, and the needle was still sitting at 0, and he opened the switch and he looked, and the needle was still at 0. But then he noticed something curious. He noticed that in the process of opening and closing the switch, he saw a little bit of the needle moving. Open, close, open, close. But when it was closed, the needle didn't move at all. So what he found was that current could be induced in a conductor if, and only if, the magnetic field passing through the conductor was changing. So by the process of closing the switch, right, I suddenly start the flow of current, right, so that generates a magnetic field from 0 to magnetic field. And in opening the switch, right, I had a magnetic field, and now that magnetic field goes away. So I can induce current, but the only way to do that is if I change the amount of magnetic field. Pretty cool. So let's take a look at just moving a conductor through a magnetic field, right? A conductor has electrons which are free to move, and of course there are protons in here too. And if I move it through a magnetic field, right, I have moving charges. They're moving because I'm moving the bar through a magnetic field, and so they're going to feel a force, right? As long as I have moving charges in a magnetic field, there's a magnetic force. And if you think about it, right, if you put your fingers, the X's here on the screen indicate that the magnetic field's into the page, the bar is moving down, right? So the force on these particles is going to be in that direction. To the right on the screen. So that magnetic force, right, if you have your right hand rule, you can see that you're going to force the electrons to separate from the protons, right, because the force, your knuckles are on the opposite side from your palm. So I get an accumulation of electrons on the left side of the bar and an accumulation of protons, really a deficiency of electrons on the left side of the bar as I move it through this magnetic field. As long as it's moving, I have that force that separates the charges. Well, once I have the charges separated, what happens? Well, I get an electric field, right? The separation of charge creates an electric field, right? Separated charge, electric field, voltage, right? So now I have generated the potential for energy. I have generated voltage. All I got to do is connect the ends of my bar now to a wire, and those electrons are going to start running, and I'm going to have current. Now, if you remember back to electrostatics, that voltage, that electric potential, is equal to the electric field strength times the distance. So we had it as delta V is equal to E times delta X. But if we think of it in terms of length, right, because the length of the bar is the separation between my charges, then I have the voltage is equal to the electric field times the length. Now, as long as I'm moving this, right, the charge will stop moving when that electric force and the magnetic force are the same. You've seen this equation before, right? We looked at it when we were talking about crossed E and V fields. But now I'm going to do something different with it. Yeah, the Q still cancels, but if I rearrange this equation to make it E, the electric field, is equal to the voltage divided by the length, and I plug that in here and I do some more rearranging, I get what's called emotional EMF equation. Remember, EMF, that squiggly E that we have here, is also the same as voltage. So I get that the voltage that is induced in this moving rod is equal to the velocity of the rod times the length of the rod times the magnitude of the magnetic field. And then all I got to do is hook a wire from one end to the other, and what do I got? I got current flowing. Now, as I move this rod through a magnetic field at a constant speed, I get voltage, which generates current if I have a loop connecting the ends of my wire. And in fact, I can calculate the current using Ohm's law, right? Ohm's law, V is equal to IR, or the current is equal to the voltage divided by the resistance in the wire. So I've just made electricity. Cool. Now, one thing I want to point out is look at the direction. So one of the things you're going to have to be able to tell me is the direction of the current that's in the loop. Well, if you think about it, right, here we're moving this bar to the right, which I guess in the pictures my camera is to the left. But if you use your right-hand rule, you would have your fingers pointing into the page, put your thumb so it's pointing to the right as it shows on the screen, and you're going to see that your palm points up. So the positive charges will move up in this bar. Positive charges, right? Because we follow conventional current, which is the flow of positive charges, even though we know it's negative charges that are moving. So our positive charges accumulate here. And so we follow the flow of positive charge in conventional current, which means that the current is flowing counterclockwise. We're also going to figure out in class, we're going to also talk about how else we can figure out the direction of the current in this wire loop here. Now think about this. Now I got current. All right, I got current running through this loop, and it's running counterclockwise through this loop. But this loop is in a magnetic field, and I have current in it. If I have current running through a wire in a magnetic field, what happens? I get a force, right? I get a force, a magnetic force, and if you use your right-hand rule, flat-hand rule, right, and you put your thumb in the direction of the current, and your fingers in the direction of the magnetic field, you'll actually see that the magnetic force is actually opposing our pulling force. And what that means is I have to keep pulling this rod if I want it to move, because as soon as I stop pulling, the magnetic force that's acting against me is going to cause this rod to stop. Now, as long as I move that at constant speed, then the force of the pull is equal to the magnetic force. So the force that I need to pull it with, I can calculate by using our magnetic force for a current carrying wire equation, FLIB. I do want to show you this, though, so let me make myself a little bigger. I have here a coil of wire, and I have it connected to a battery. Well, okay, now I'm going to connect it to the battery. And I'm going to put this iron rod here into this wire, this coil, and we're actually going to do this in lab. If I pull this, notice how the coil pulls back. So I am pulling, and as you pull this, you can feel the magnetic force pulling back at you. And if I let it go, whoops, the magnetic field exerts that force that pulls it back in. Pretty cool. So if I want to keep this moving, I better keep pulling. All right, let's take a look at a couple calculations. I have a rod that's moving at a speed of 1.6 meters per second. The rod is 30 centimeters long and has a resistance of 2.5 ohms. The magnetic field it's in is 0.35 Tesla, and the resistance of the U-shaped conductor that this rail is moving on is 25 ohms. So the first thing I want you to do is calculate that induced EMF. Calculate the motional EMF. So remember that EMF is equal to VLB. So take your velocity, multiply by the length. Now the length you're using is the length of the rod, right? That's what we're moving. So that's at 30 centimeters, but put that in meters. And multiply by B, the magnitude of the magnetic field. If you do this right, you should get 0.168 volts. Not a lot of volts, but hey, I got some voltage. Well, now that I got voltage, I will have current. So what is the current in the U-shaped conductor? Well, we're going to use Ohm's law, right? Current is equal to the voltage divided by the resistance. So we have our voltage, but what's the resistance? Is it just 25 ohms? I mean, I only want to know the current in the U-shaped conductor. Well, current runs through the whole thing, right? And current is dictated, the magnitude of the current is dictated by the total resistance of the circuit. So I have current running through my circuit, and it's not just encountering 25 ohms of resistance from this U-shaped conductor, but it's also encountering 2.5 ohms of resistance from the bar. So I need the total resistance, and there's no junctions here, right? The current is just running in this circle. So that means that these are in series. So I need to add together the resistances. So my voltage, 0.168, divided by the total resistance, 25 plus 2.5 ohms, will give me a current of 6.1 times 10 to the negative 3 amps, or 6.1 milliamps. One more question. I want to know, what is the external force needed to keep the velocity constant? Well, to keep the velocity constant, right, the forces have to be equal. So my pulling force has to be equal to the repulsive magnetic force that's trying to stop me. So the force of pull is equal to magnetic force. Remember, magnetic force is flib for a current carrying object. So force, ILB, so we have our current. Now the length we use is the length of the bar, right? That's what we're pulling on. We're pulling on the bar. So we need that 30 centimeters, put that in meters, and multiply by the magnetic field. And there you go. There's your pulling force. It's a small force, 6.4 times 10 to the negative 4th newtons. So that's going to be hard to do at constant speed. I might accelerate this bar if I was pulling it myself. All right, let's talk about this whole idea of the changing magnetic field. So cool. Faraday found that current is induced. We can make current if we change the amount of magnetic field passing through a coil or a loop, right? We need a coil or a loop because we need the current to flow, right? We need a loop for current to flow. How much current is generated will be affected by the amount of magnetic field passing through the loop. And of course, that depends upon the orientation of the loop to the field. All right, if I pretend that this roll of tape is my loop, right? If I have the magnetic field passing directly through the loop, I've got a lot of magnetic field passing through it, right? If it's perpendicular to the magnetic field. But as soon as I start to rotate the loop, now I start to lose the magnetic field. You can see that by looking at how many magnetic field lines are penetrating this loop. And then when the loop is actually parallel to the field, or the plane of the loop is parallel to the field, right? Now I have no magnetic field passing through the loop. So orientation matters. The area of the loop matters, right? A bigger loop will have more magnetic field passing through it. So this idea of magnetic flux came to be, and what magnetic flux is a measure of the amount of the magnetic field that passes through a loop with some area. So let's take a look at its equation. So we look at a uniform magnetic field passing through a plane or a loop that has a surface A. Magnetic flux then, and it's symbolized by this big capital phi here, is equal to the magnetic field B times the area A. Now that's true if the magnetic field here has the loop here has all of the magnetic field passing through it. But in order to get that, this is not going to generate current. I'm going to have to change the amount of magnetic field, and I could do that by rotating my loop, right? As I rotate my loop, the amount of magnetic field passing through it starts to change. So I need to include the fact that as I start to rotate, the amount of magnetic field changes. So I'm going to add this angle here, the cosine of this angle. Now what is this angle? Well, this angle is the angle between the normal to the loop and the magnetic field vector. So a normal to the loop, right, would be perpendicular to the surface of the loop, just like a normal force is perpendicular to a surface. So my normal to my loop would be like if I take my pencil here and I put it through the very center of this roll of tape. So as I rotate it, right, my normal to my loop starts to rotate. And so we take the cosine of the angle that this normal line makes to the magnetic field vector. Now, magnetic flux has a special unit, and it's the Weber, WB, Weber, named after Weber. A Weber would be equivalent to a Tesla times meter squared, right? That makes sense because magnetic field is Tesla and area is meter squared. All right, last bit. I know this is getting long. So let's go back to what Faraday observed. He observed that changing magnetic field or changing flux affected the amount of voltage and current running through a conductor. So he found one, right, that motion-induced EMF. So if he moved the magnet in and out, or he moved a coil through a magnetic field, this produced voltage. He observed that the direction that he made the motion affected the direction of the current. So running a magnet one way through a field and then maybe pulling it out the other way changed the direction of current. This is something we're going to take a look at in class. He also found that the amount of voltage was proportional to how fast the change happened. So he said to the rate at which the lines are cut, right, the magnetic field lines are cut, well, that's the speed, right? How fast the change happened affects how much voltage is produced. And that the more loops of wire he put in his coil, the more voltage he got. So that leads us to our last equation, which is Faraday's law. Faraday's law says the voltage is equal to the number of coils times the change in flux over the change in time. So remember, flux is magnetic field times area. So that change in the flux, the magnetic field or the area, divided by the change in time, so how fast that happens times the number of coils, gives us the amount of voltage. Now, you might wonder what that negative is all about. Well, that negative sign we're going to talk about in class when we talk about Lenz's law. What we're going to find is that the voltage that's generated is actually generated in a direction to oppose change, because nobody likes change, not even coils and wire. All right, write your WSQ form, and I'll see you in class.